Bonjour à vous, bon après-midi, good afternoon to you. It's a great pleasure and a great honor to welcome you to the International School of Astrophysics Daniel Chalonge and to Observatoire de Paris for this Paris Nobel Conference 2006 in the honor of Professor George Smoot and celebrating the discovery of the anisotropy of the cosmic microwave, or so-called fossil radiation of the universe. This conference is co-organized with Héctor de Vega here from CNRS and the University of Paris 6. We thank all of you for coming to this conference, for being present here. Distinguished scientists from many places of Europe and the world, and distinguished personalities, and among all, I want to especially welcome Professor Claude Quentanouche from École Normale Supérieure, Nobel Prize of Physics. Professor George Smoot has been awarded the Nobel Prize this year for the discovery of the anisotropy of the cosmic microwave background radiation with the COVID satellite in '92. This keystone discovery ushered the era of precision cosmology and set up the basis of what is called today the standard model of the universe, or so-called concordance model of the universe. Cosmic microwave anisotropies are explained by inflation, and in this sense, microscopic quantum fluctuations of the order of the scale of inflation, namely 10 power 25 centimeters, are stretched into microscopic fluctuations of the astronomical scale today, namely 10 megaparsec, namely 10 power 25 centimeters. Such extraordinary transition from microscopic scale to macroscopic astronomical scale, transition from quantum fluctuation to classical macroscopic fluctuation today, was not observed before, never before. This is in concordance with the large-scale observations, and this is the reason why we placed this conference on the celebration of 15 years of the understanding of formation and evolution of the universe, in some sense from COVID to MAP, to the Wilkinson microwave anisotropy probe, which was the project continued the effort of COVID. Professor George Smoot has regularly lectured at the Chalonge School and participated in all events of the school, courses, colloquia, workshops, having the record of participation in the board of lectures. We here have been many times stressed that, and today more, because it's the first time he's received here with the Nobel Prize recognition. The International School Daniel Chalonge is very proud and delighted of Professor Smoot's achievement, and we express him our warmest congratulations. Professor Smoot, please.
Thank you. It's a pleasure to be here, especially be in this room again. It's always a special treat to come into the Observatoire and do that. And I had two special treats lined up for you today, but I wasn't able to get to download. I have a video which was released. Oops, I need to stand over here. So I have a video that was released just after the ceremony, in which I have the California Music Band perform the Big Bang, as a music video. And you can go to this website and find it, but there's a better version that will be released in January, which was taken by Swedish TV and shown during the banquet, to my embarrassment. But that's the case. But it starts out with the 220 people compressed into a very small region, and then the universe expands and galaxies form, spiral and elliptical galaxies form. All the time music is playing. It starts out very fast tempo and it slows down as they get far apart. It's interesting to watch. And the impressive thing is, I got up on this little rickety ladder out here, up really high, and I explained it to them, and they did it in one take. And they had suggested the students in my lab do it, and I said I didn't think they could do it, but the band could, and the band did. So I'm sorry I don't have it here to download. When I get the DVD, then I can show it, but I recommend you see it, although it's kind of strange, but so forth. Yeah, I'll just move that out of the way, right? Okay, the other thing I wanted to tell you that was different is that we have formed a Center for Cosmological Physics. Merry Christmas. And this is a brand new thing, and we have an ad out to looking for outstanding people. We have an ad out for postdoctoral fellows, and the deadline for this ad is actually January 1st, so if there's any great postdocs in here, please apply right away. And we're going to be looking for grad students, visitors, and collaborators, so I wanted to announce it, even though this is not officially announced, but you can look on the various websites and you'll see the job already listed. So it's not a secret to scientists, it's a secret to the rest of the world. And when we announce it, I thought I'd tell you a couple of view graphs from the inaugural meeting. Guess I can try and move over to this side so I don't have to keep walking in front of it. So this is a view graph that was made in November, the first time we had a meeting, and we say we'll make a public announcement in March. We were expecting Stephen Hawking is coming to visit us, and he will help in the announcement of the center and give a public lecture and so forth. And so what is it we're trying to do? Well, primarily we're trying to address the question of what physics do we need to describe what we observe of the universe, not what's all the correct physics and everything, but what do we absolutely need to have in order to make things work. We're going to focus on research, we're going to focus on education, and we're going to focus on outreach. We have three things we're doing, and it's quite extensive. I won't go into them in too much detail. And how we're going to start out on the research is we're going to make a flow-down research plan. That is, we're going to produce the minimum straightforward standard model of cosmology. That's a takeoff on particle physics for those that don't know what the minimum symmetric model. But so then we're going to define what are the open questions in cosmology and to make a roadmap to answer the questions. And we'll take either existing programs and modify them or create new programs, and we'll collaborate with other centers and other institutions in order to make sure that these kind of measurements are going on. And so, what's this going to be? This is a standard by which we compare all the alternate models, but also the one that we believe now describes things. We have a good idea what it is, and when you look at that model, you find out that we're in the situation that we were. The example that I try to give is when people did the various measurements and found the ideal gas, basically led up to the ideal gas law, they had a macroscopic description of how an ideal gas behaved, and then it wasn't until later that people got a microscopic description that explained what was really going on. And that's sort of where we are in cosmology. And so I go down and I list what I think are the 8 great open questions that we have in cosmology. The first is, did inflation happen? If it did, how did it happen? Right? We need something like inflation. We make a model of simple version of inflation or variations of inflation, and we can compare them to the observations, and we can describe everything we see right now, but we still have to do it. There's also the same thing happening for the question of dark matter and dark energy. We know there's dark matter, but we don't know what it is, and we don't know how it behaves. But you put the simplest possible model in for dark matter, and it describes the results we see as well as possible. It's unlikely that's the true version of dark matter, but it's a starting point that it works macroscopically. We don't know what the microscopic is going to. Likewise, the dark energy is even more mysterious. All we really know is the universe is accelerating, and if we put in a simple model, there's a certain amount of energy in each part of the vacuum. So it's a cosmological constant or constant vacuum energy. You can describe all the data we have, basically. And so same things happen. So we have this problem that started me in the first experiment I did. It was cosmology oriented, which used to be where is the antimatter, and after searches it became what is the why is there an excess of matter or antimatter? Because in the early universe there were equal amounts, and in the present universe matter dominates, right? So you have these series of questions, and you go down these. Then they get more complicated. Are there extra dimensions? Do the fundamental constants vary? Are there other forces? There may be 2 or 3 kinds of dark matter that interact with each other, but those forces don't interact with other particles, and that would make the dynamics of galaxies a little more complicated than we see, but we haven't measured it carefully enough to know. And so these are the questions that came to me, and when I talk to my colleagues, those are the big open questions that show up. We have a rough macroscopic description. We want to define more carefully, is that macroscopic decision will match what we see? And then if it does, then we know what kind of microscopic physics to be looking for to explain it. And so this picture's about, what the thing that's kind of weird. If we look at radiation, we look at ordinary matter, there's a certain pressure and attractiveness under gravity. The gravity is attractive, that is, things tend to slow down when they move apart. But if you have other kinds of things, gravity's repulsive, and things tend to pick up speed as they move apart, right? That's strange, right? This stuff we're used to, this stuff we're not used to, but we believe that 70% of the universe is in this category. And so this is one of the sort of mysteries that's open. So when we say, when we talk about precision cosmology and the advances we've made, we've gotten to the point where we can do calculations fairly accurately, and now we realize we can calculate, but we don't really understand, right? I mean, we know, but we don't know. That's the kind of thing. It's like we use the ideal gas law, but we don't really know what all the molecules and everything are doing. It wasn't until later when we understood statistics and mechanics and put it all together that we had a microscopic understanding of what's going on. So this is just showing the universe full of springs under tension or whatever it is and what's going on, just as an example, and why this is going on. So I just wanted to show you that there's a whole series that I'm skipping through, I hope. And so the next step we're going to do, once we've defined the model and the questions, is to develop a roadmap. And some of the questions, when you look at them carefully, actually all address the same thing. One of them, which is general relativity the right model of gravity? Right? That's one of the questions. Is it sufficient on the large scale to explain what's going on? And if there are extra dimensions or if there are other aspects to it, that's something going on. So these become meta questions that span across more than one of the major questions. And so, but this is something that people have done in other areas, that is address a major problem and then make a roadmap on how we're going to answer the questions to get to the point where we think we understand things to a level that you could be confident that you really are following along. And then you go on and augment your program, so I skip on that. But the other activities we think are actually extremely important is being able to prepare for the next generation. And for our center, we're focusing on middle school through postdoctoral level. We have to attract the next generation in. A lot of the theory is now that people who are in their 4th and 5th grade, that's when they differentiate and start liking science. You have to get them to think science is good then, but if you're going to get them to become scientists or engineers or software people, you have to retain them all through middle school, that is 7th, 8th, 9th grades, all the way up through into college, and you have to keep them going. So it turns out to be very important. You have to attract them in, and then you have to help them succeed. And so we're going to do a bunch of things that start at the top, which is at the Center Fellows, and they're going to they help the next level down, which is the grad students, and they help other things. And so we have a link to another project we're starting, which is the Teachers Academy. We're hoping to have partners in other parts of the world that have matching Teachers Academy. We have teachers come there, get teaching materials and learn during the summer and go back to their schools and teach, but then we support them through the web and through other things. And so we have an education program, which I was going to show you, that we have this thing where we try to develop the entire history of the universe on one page, an explanation, and then a website that students can go to and try and understand how the universe evolves step by step, including quizzes and everything else, and teachers and material to help teachers along the way. That's part of the issue. And we also want to have outreach. That is, we think that we have to be ambassadors of science. Cosmology is one of the things that's very attractive to a wide-ranging audience, and therefore, by going out and giving talks about cosmology and about how science is done, we believe that actually makes the entire public more aware and more interested in science. So, and I have an example of the kind of things you can do in terms of going out and talking to people, providing web-based materials, and providing handouts. And one of the things that I cite as a really good handout is what I call the WMAP beach ball. Okay, so Olivia I assume you were involved in that. But it's basically, they made inflatable plastic models of the microwave sky, and they sent it out, right? And they're just about any office of most scientists you go to, you'll find a copy these days. Those are the kind of things we have to do. I have many more pages on education and outreach. I assume that's not what people came here to hear about. It's something that I care about and want to do. So let me switch back to the talk, which is sort of how the lead on to how anisotropy was found. So we'll start with this. So this is the WMAP beach ball that shows the quantum fluctuations in the early universe, what we believe were quantum fluctuations in the early universe that become the seeds of galaxies and clusters of galaxies and clusters of clusters of galaxies. And it's revealed through the cosmic microwave background. So I make this so you appreciate that it's actually hard to see the cosmic microwave background. You have to actually pay attention and in order to see it. But the story starts about 40 years ago. Not that there weren't hints and other things going on earlier than that, but it became very clear because of the careful work of Robert Wilson and Arno Penzias that there was a radiation that came from beyond the Earth and their instrument, and beyond the galaxy came from the universe as a whole. And this is we call the fossil radiation, or the relic radiation from the Big Bang. That is, this fading glow from a time when the universe was much hotter and denser. And there's a lot of lore about what was going on. This was a radiation that was actually predicted by Gamow, Alpha, and Herman back early, and then was reinvented and repredicted by Peebles under the direction of Dickey. And when Penzias and Wilson made their discovery, it was immediately, fairly quickly communicated to the Princeton group, and two papers were put out, one about the discovery and one about the interpretation of the discovery, that appeared in the journal in 1965. And so this is the beginning. This is the beginning. In the early days, this was called the fossil radiation, right? It was called the relic radiation or the fossil radiation, or just simply the 3 Kelvin radiation. And they actually measured 3.2, but they rounded it off to 3 Kelvin and so forth. And so my early exposure to this came when I was a graduate student at MIT doing particle physics. Joe Silk, who some of you know, because he's part-time in Paris and part-time head of astronomy at Oxford. But he was a postdoc at Harvard University, which is just down the road from MIT. And he started working on the problem of how the universe was made. And it was at a time when we didn't know anything. And so the title of this paper he wrote in 1967 and he gave talks about was Fluctuations in a Primordial Fireball. And it starts out in the abstract. One of the overwhelming difficulty in realistic cosmological models is the inadequacy of Einstein's gravitational theory to explain the process of gravity formation. And of course, my colleagues who were working in an advanced field, particle physics, they were laughing, saying, what is this field? You know, that it does, they can't even, you know, there are galaxies there and they can't make them, right? And it turns out to be a serious problem. And the thing that was sort of novel to me was I had heard of this fossil the 3-degree radiation, and I kind of thought of it as the flash from the Big Bang, just like when the camera goes off, there's a flash, there's this flash. And what's been pointed out by Jim Peebles and then followed up by Joe Silk was if this 3-degree Kelvin microwave background, as it was called at that time, if it existed, it so dominated the early universe that it prevented any structure from existing, it prevented any matter from existing in any reasonable form, that if you go backwards, and as the universe, further and further back in the history of the universe temperature goes hotter and hotter. There comes a time that we study when the temperature was about the temperature of the sun. But if you go back further, it was 1,000 times that of the sun, you know, and then 1,000,000. So 1,000 times brighter than the sun is a famous quote about the atomic bomb, right, and so forth. But it was then 1,000,000 times and then 1,000,000,000 times brighter than the sun. It was so bright that if you took this laser pointer in it, it would be vaporized and turned to plasma almost instantly. So that any structure that existed, any matter that existed, was completely ionized and completely smoothed out in the early universe. And so the problem was this very radiation that we're seeing would destroy anything that existed. It would erase it and homogenize it in the early universe, and eventually it would reach the point where the energy is exchanged and you make positron and protons. I mean, you know, you would make positron-electron pairs and they would start to dominate the universe, and then proton-antiproton pairs as you go back. Eventually you get a universe that's completely this uniform soup, all species equally populated and so forth. And so the question then is, once the matter and radiation decouple and the temperature gets down to around 4,000 degrees, then could there be fluctuations left? Could they survive this early fireball, right, 1,000 times hotter than the sun? And if they did, could they be sufficient to make galaxies? And so that leads to Joe Silk's calculations about what happens to fireball, you know, what happens to the fluctuations in this fireball. And so he invented one of the things that was called after that Silk damping, the fact that the radiation was blowing things around. Fluctuations that were on too small a physical scale will be damped out. They will oscillate around and get smoothed out. That's called Silk damping. And you'll see an example of that later on. But the question he ended up posing is, would the fluctuations survive the primordial fireball to the epoch in which galaxy formation was possible? And that's a period which is roughly 1,000,000 years after the beginning of the fireball. Right? That's the scale which when you can first start forming galaxies. And this was kind of a vexing problem. And my colleagues were laughing and saying, you know, why is anybody working in this area? You know, you can just make it all up. They don't know anything, right? And you know, and I'm saying, well, this really is a field that if you can go and make observations in it, you're going to make good discoveries, because either you can prove that this 3-degree Kelvin radiation did not come from the fireball, right, and the Big Bang is wrong, right, somehow there's something else, or you can use it to learn about the early universe, you know, and somehow know that there will be fluctuations and galaxies will form because they are here, right? And so I said, when I got through with my research and got my thesis done, I would look for a way to get into this field, because this is a field that you could be a pioneer in, right? So, okay, so, and I started thinking about it, and, you know, having been a student with a rigorous education from MIT, I said, okay, what is the radiation? It's an electric field with a cross-magnetic field, and it's here, and it has certain properties. It's got a frequency dependence, it's got an angular dependence, and it's got a time dependence. And you go through it, that's all there could be, except for the polar, you know, the orientation of it. And so the frequency dependence is what we call the frequency spectrum, and it's predicted to be the thermal spectrum. If there was a hot Big Bang, it will have the black-body spectrum, the formula given by Planck, right? So that's the prediction you have for that. The angular distribution on the sky should be uniform to first order, but there have to be at least the primordial fluctuations left to form the galaxies and clusters of galaxies. So it would be uniform, but there have to be some seeds at some level, right? You can measure the polarization, and the answer is to first order there should be no polarization, but in 1968 Martin Rees had worked out if there are seeds, then the local anisotropies will cause small amount of linear polarization, and you could look for that. They're very linked to each other, right? Now later on we'll understand, in one of the few theory papers I wrote, that you will get a different kind of polarization if there is inflation produced gravity waves, and so it turns out to be that way. The other thing that I did experiments in that was never that promising was that the time dependence should be twofold. One, the universe is expanding, therefore the temperature of the radiation is decreasing by the expansion. So there should be a 1 plus z, which is the scale factor of the universe, changing of the temperature of the radiation. So if you're able to sample the radiation at a great distance, you're looking back in time, the temperature should be higher, and the further out you look, the higher it should be. Just exactly linear with the expansion rate of the universe. The other thing is the photons should come in with the statistics, which is given by the thermal distribution, which is known as Bose-Einstein. That is, the variance has an interference part as well as a counting noise part, just the fluctuations of n. So it turns out the variance goes as the occupation number squared plus the occupation number for those that are technical. So in the long wavelength region, the occupation number is greater than 1, so the n squared dominates, and in the short wavelength region, the n dominates, and so Poisson statistics, and you have intermediate. So we did a series experiment like that, and there's even some coherence length that, like Hanbury-Brown twists interferometers, so you can run these kind of tests. And then something that I hadn't been thinking of, but a paper was written by Rashid Sanyev and Zeldovich in 1972, saying that if you look at clusters of galaxies, not only are there matters in the galaxies, but there is a lot of material which is between the galaxies, and it's moving with variable velocities, and those velocities correspond to energies that are well above the ionization for that material. It gives keV kind of range. So there are lots of free electrons in clusters. The radiation coming from the distant universe passing through these clusters, if it does come from the early universe, is occasionally going to be scattered. Typically 1 part in 1,000 and 1 part in 10,000 of the photons are scattered, and they hit these hot electrons. On average, they go to higher energies. That means the cluster leaves a shadow. At long wavelengths, the cluster leaves a shadow. That means the radiation came from behind it. So if you see this effect, the radiation is coming from cosmological distances. It's sort of proof of the non-locality of the radiation. It doesn't come from every now and then I get these newspaper articles or stories that people have published that it's a local effect from our own galaxy, and yet we have plenty of evidence that it came from far away. So Rich Muller and I, who were young postdocs at the time, proposed to go down to use the NASA Deep Space Net at Goldstone, a great huge telescope, and they just recently invented a maser receiver, which had very low noise, and we went to look at the coma cluster and see what we can do. We didn't quite have enough sensitivity to make a reasonable measurement. And this is the beginning, 1972 is the beginning. This year, within the next year, you're going to see a dramatic change, and the Sanyev-Zeldovich effect will become an important cosmological tool. And if I get to the end of my talk, I will show you the reason why that is. Basically, is finally people have dedicated to build receivers and big telescopes in order to make these measurements, because clusters of galaxies as big as they are tiny on the sky. They're arc minutes on the sky, not degrees on the sky. So you have to have a big receiver and so forth to detect them. Okay, so I'll talk about the development of the CMB research. Most of that went on in the United States, and it either went on the East Coast or the West Coast. And the West Coast was Berkeley, and when I finished my thesis in 1970, I started looking around for jobs, and I did a number of interviews, a number of offers, and most of them were to continue on doing what I was doing, that is work in particle physics. But one of the people that I interviewed with was Professor Louis Alvarez and his group, which was a very famous group at the time in particle physics and called Group A. And he had decided that he knew, like all the other particle physicists, that matter and antimatter are created in equal amounts in any big interaction. Therefore, the universe had to be equal amounts of matter and antimatter. Everybody knew that. So where was it? We should look for it. It's not on the Earth because the Earth doesn't blow up. There's no annihilation going on. It was probably not in the solar system because we see comets hit things. We occasionally have sent a probe to the moon and so forth at that time. So The only sample of stuff that was from outside of the solar system that we knew about were the cosmic rays. So he wanted to build a detector that we would put in a high altitude balloon and look at the cosmic rays coming in and determine were they matter or antimatter and what their charges were and so forth. And I had been trained as a particle physicist, but my experiment had used what's called a magnetic spectrometer. We run charged particles through a magnet and we see them curve, and we did their tracks and did the fitting. That's exactly what we needed to do for this experiment. So I was able then to make a partial transfer, use my technical knowledge, but move into this new field of cosmology, answering the question about the excess of matter or antimatter. At the time, we thought they were just segregated a little bit. I did a set of experiments. The first experiment, we got several thousand cosmic rays through our spectrometer, and we saw no evidence of antimatter for anything of a charge greater than 1. We would see electrons and positrons, and we would also see protons and antiprotons. Those can be produced by high-energy cosmic rays hitting another nucleus, and you produce a proton-antiproton pair or electron-positron pair. They're fairly common, but looking for antihelium would mean if you saw antihelium, you put the numbers in. It had to come from the Big Bang, any matter of the Big Bang. And if you saw anti-carbon, nitrogen, oxygen, that would have to come from anti-stars. And so we decided to concentrate on those. And we did the first experiment and got down to about 10⁻³ level statistically. We needed an improved experiment and got down to better than 10⁻⁴. And I decided that at that point, the question had changed. It was no longer where's the antimatter, it's what caused there to be an excess of matter over antimatter in the late universe when they were equal in the early universe, right? And so at that point, Louis Alvarez had taught us, whenever you finish an experiment, look around to new technologies and new ideas and think about what you should do. He was expecting us to think about completely new approaches to looking for antimatter, which some of my colleagues did, but I thought, here's the chance to get back to the fossil radiation and see what's going on. And so he didn't think that was so wonderful, but he thought young people should be given a chance, and I should get some seed money and some backing and access to people, and so I could start up, and if it worked, then I could get more money and continue on, and that was just a good thing. So what happened at Berkeley was Joe Silk had started in 1970, and he was there giving talks and talking to us, and he convinced Professor Paul Richards, pictures I'll show you in a minute, to take on a couple grad students to start working in this field. He took on a person named John Mather, who shared the Nobel Prize with me a few days ago, and Dave Woody, beginning in the early 1970s, and they started developing bolometers, that is the kind of detectors that we're going to be using on Planck, and on the HFI particularly. He started developing them and improved them quite substantially in order to be sensitive enough to measure the cosmic background. And he also started adapting the Michelson interferometer to make a very careful measurement. And these turn out to be a precursor for the best spectrum measurement ever made, which is the Jacobi-Fires measurement. First, it was training the students, and second of all, it was developing the technology, and I'll come back to that a little later in the talk. I started experiments on anisotropy and polarization in early 1970s. Started with ground-based. As soon as it worked in the ground, we moved into the air, into aircraft, into balloons, and eventually into the spacecraft, right? So this is precursors for what's going on. And I started a long wavelength collaboration, spectrum measurement collaboration that was Berkeley, Italy, and then we were joined by Haverford College in 1977. I'll show you pictures of that. There we're working at long wavelengths and developing low noise coherent receivers and getting them improved and working with industry. We also were developing reference loads and materials to use for reference loads that again turned out to be very useful later in the field. Okay, and we had competition that had a head start. And why did they have a head start? Well, Penzias and Wilson discovered it completely out of the blue as far as they were concerned, but as soon as you have a great discovery like that, theorists start working on it. They start telling you what exciting things you could do with this new thing if it's the right thing. And Peebles was at Princeton and giving talks and encouraging his colleagues, particularly Dave Wilkinson at MIT, but also Ray Weiss, who had been a student at Princeton and moved to MIT, and he was working with Doug Mulder, and they were starting ahead of us in terms of these observations. Okay, so here's a picture of Dave Wilkinson. And here's a picture of his early apparatus somewhere in the late 60s, set up on White Mountain. You're going to see we keep going to the same sites. They're high, dry sites, either on top of mountains or on top of Antarctica or up in space. So here are the radiometers. This is a spectrum measuring device. One horn looks at the sky, one horn looks at in a cold load. There's a couple of circulators. Those of you that ever knew Dave, you'd understand this. You see the same thing again. Horn facing one way, horn the other, and the sky horns to make a cold load over and over again for the different frequencies. Here's what the equipment looked like put together. Right? It's surrounded by a ground screen, and then here's the thing looking at the sky, and then you bring in the cold load there in order to do it. And it's pretty crude, but this is 1968, right, or something. It's, there were hippies in San Francisco. Okay, so what's the issue here? Well, at the time, we knew in the cosmic microwave background, we quit calling it the cosmic background radiation in those days and called it the cosmic microwave, because some of our friends said there'll be an infrared background, an optical background, everything. You guys can't have the only cosmic background. But in fact, it is the only cosmic background. Just go in the early universe and it's, go to 1 second and there's nobody else, right? And so, but anyway, the predictions in those days, in the 1970s, was that the anisotropy signals, the things that were going to produce the galaxies, clusters galaxies, should be at about 1/1000th of a degree out of a temperature of 3 degrees. Turns out that was a really optimistic estimate, right? But the receiver temperatures in those days was usually a few, which few is somewhere between 5 to 10 times 30 degrees. So they were between 150 and 300 degrees for reasonable ones. And that produces a noise compared to the 3 degrees, which produces a noise compared to the 1,000 degrees. So the noise is very serious. The Earth is a temperature of 300 degrees. So the signal was going to be at least 1 part in a million of the other signals that were just floating around that you had to see or you had to exclude. And so you had to develop a more careful technique. And that technique is to compare whatever you're seeing with signals of the same level. That is something around the same temperature of 3 Kelvin. And also to exclude, reject, average out, or otherwise get rid of the signals that are a million times stronger in such a way that you really know what's going on. And so that's tricky, and this is just to show you it's trickier when there's other stuff there. Reading is harder when the backgrounds are confusing. And so here's one of the things we developed. This was a substantial sophistication over a thing that Bob Dickey had invented in the 1940s to try and make temperature measurements in the early days of making receivers. He invented well, it wasn't microwaves, it was macrowave receivers. And the idea he did was chop between two things in order to be able to measure the temperature difference very quickly compared to the fact that the receivers were drifting all over the place because they weren't made stable enough and so forth. So the basic idea for the differential microwave radiometer is you have 2 equal inputs that look at different parts of the sky, and you compare one part of the sky with another part of the sky. That is, you're comparing 2 things with roughly the same temperature, looking for the microscopic difference. You have a switch that switches rapidly between them. In this case, in the old days, because low frequency receivers were much more lower noise than high frequency receivers, we would have a local oscillator and down convert the frequency by beating them together so that we would go from a high frequency like 30 gigahertz down to a half of gigahertz, that is a factor of 30 in frequency, so we can amplify. And so then you have a series of amplifiers, and then you have a detector, that is something that detects the total energy, and you look for changes in the signal that are synchronous with the switching back and forth. So if you switch with a square wave, you expect the signal to be changing with a square wave. You look for the step. You don't look at the absolute value. So if the absolute value is drifting around, but there's a step on top of it, you can still see it. And so here is the thing in the flesh. These are standard gain horns. This is an actual switch, electromechanical switch. This is an isolator. This is the local oscillator. There's a double balance mixer here, which is a trick you use in order to get rid of a lot of the noise by double balancing and differencing. And you get out the low frequencies. The low frequencies are amplified here, then they're amplified again, and then they're detected there. And there's a box not shown, which allows you to do it synchronously. Nowadays, we have receivers that work up to very high frequencies, and we don't down convert, we just amplify them straight through because we've improved the noise. And so the only difference between this one and this one is this thing called the corrugated horn antennas. And I explain why that is. The standard gain horns that I show on the right, they have your classic diffraction issue. If you have a horn, it connects to a waveguide. In one direction in the waveguide, there's an electric field that's uniform across the waveguide, and the other way it goes as a simple cosine or a sine wave, depending on how you started out. And when you look at the far field pattern, It's the Fourier transform. You get your sine x over x. So this is a polar plot. This is 90 degrees in one direction, 90 degrees in the other direction. This is where the main beam is. The signal then goes down. You see the sine x over x, this little wiggles. It's down by a factor of 10, factor of 20, of 100, factor of 1,000, a factor of 10,000. And then the plot runs out. And you'll notice how far out you're down by only a small amount. Whereas if you look in the opposite plane, the magnetic field plane, you get down to 10 to the minus 4 with a fairly reasonable angle, but there's some extra noise down there. And so you cannot make the measurement, since the signal is 1,000,000 times stronger, you cannot make the measurement with a horn like this. You have to have shields to prevent you from seeing the Earth and so forth. Because even if the Earth is 90 degrees off axis, it's still 1,000,000 times stronger than the signal you're looking for. So even if you 10 to the minus 4, it will be 100 times stronger than the signal you're looking for. So you have to develop some new technology. There were two approaches, the approach that I decided to take and the approach that the East Coast decided to take. And I decided to go back and study antenna theory very carefully and trying to figure out how I could get the E-plane to look like the H-plane. And what you had to do was, instead of having uniform illumination across it, you had to taper it. And the way you could do that is by putting corrugations in to force the electric field to be 0 at the edge. And when we did that, well, after a lot of work and then did that, here are the beam patterns: 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, 10 to the minus 4, 5, 6, 7, 8, 9. And it turned out we needed all 9 decades by the time we got to making the careful measurement. And you see the E and the H planes are very symmetric in terms of what's going on, which is also an advantage in the kind of measurements. So we did this approach. I will show you the opposite approach in a few more slides. And we developed it. And at the time that we were developing this receiver to map the radiation, Tony Tyson took sabbatical from Bell Labs, where he was working on designing ways to detect gravity waves, and he was an expert in low noise systems and in vibration isolation and so forth. And he came and he was my roommate part of the time, and I turned him to the other side to ask him to help design our receiver in order to make it so there was vibration isolation and low noise. We didn't worry about cables moving around, so forth. There was a lot of tricks that he knew. And so the 4 of us ended up coming up with this design, and with help from technicians that Louis Alvarez made available, some of them out of Group A. These bottom 4 people out of Group A, I hired John Among to write the software. And then many of these people stayed with me through a whole long sequence of experiments after that. But it was the fact that Louis was able to back us to get startup money, but the fact that he gave us access to these people with such technical skills that made it possible for us to be successful in the early days. So he incubated us the same way that startup companies in the Bay Area, the venture capitalists will give them money, and then they put them in an environment where a lot of they're serviced by managers and accountants and other people to help them in order to get the companies off the ground and get started. He did very much the same way to many different people in his group. And out of that group, a lot of interesting projects started. The Supernova project got started. There were the work on the dinosaurs that Louis himself did. There were a bunch of projects that got spun off that weren't traditional high-energy physics, but turned out to be very productive. So this is the actual differential microwave radiometer we made. You saw the pictures of this one before. This is our atmospheric monitor. It runs in the 50 to 60 gigahertz range. This particular one is 54. That happens to be on the edge of a bunch of oxygen lines. So you can measure whether the atmosphere is the same on either side. And this is a 1 centimeter wavelength corrugated horns designed to measure 1 centimeter wavelength. And there you can see the differential part. There are 2 horns. And it's designed to rotate around because the 2 horns may not be identical. So we exchanged the horns by rotating the whole system around. So we had to have this complicated rotation system, which had a chain drive, and a very complicated thing because it would quickly accelerate up and spin around and then slow down and come to a stop very slowly, so as not to leave the whole thing vibrating, hitting against the stop. So it was a very careful thing, and you could see all the wires and the cables and the whole thing set up. Then you can see it when it's actually sealed up, getting ready for flight. You see we sealed it completely, and this is part of the screws are in. We put screws in everywhere so that the RFI can only come in through the horns or through these quarter wavelength windows. And this whole thing is then set up so it can do it. You put the airfoil on because this is flying on an airplane. This is what it looked like when it was taking data. This is what it looks like when it's stowed for takeoff or landing. You'll see the thing is rotated 90 degrees, so the horns are underneath, so no water or dust can fall into it until it gets up to high altitude, and then you rotate it into place. Start taking data. Here is the aircraft on which it flew. This is all the experiments that this aircraft were doing. You will notice all of them along here, here, and here. Our experiment in front. All of these are downward looking. They were designed to take photos or infrared images and so forth, looking down. This particular airplane made a couple flights from Turkey to Scandinavia, taking pictures of interesting objects on the ground. And then one of the U-2s came down out of the sky in the Soviet Union, and Gary Powers was arrested. And it was then released to civilian duty because there was an agreement it would not fly over the Soviet Union anymore. But it was designed to fly very high, very stably, so it could get very good pictures. And that was perfect for us because we wanted to look the other way and get very good measurements of the sky. And we needed to be very stable. We couldn't have it listing, so looking through more atmosphere on one side than the other. And we needed to be able to rotate around and see that we're seeing the same thing, flying in a nice straight line, and see what we're doing. And these pilots were exquisitely trained to fly over certain trajectories, to know exactly where they were, and so that they get good pictures on the ground. We're just trying to get good pictures of the sky. So here's a picture of our apparatus being lowered into the spacecraft. This is such a carefully engineered plane that we had to have this structure on here because for the integrity, the airplane depended on being pressurized slightly. The skin effect gave it some of the structural rigidity. It was basically a fuel tank, a pilot holder, and a jet engine, and big wings. So this is it being assembled. This is me, and this is Steve Plain, one of the grad students. Mark Gorenstein took this picture, so he's off in the distance, and you can see it being loaded into a NASA plane. This is part of the many collaborations where some Department of Energy funding and then using facilities either of NASA or NSF, we ended up making series of measurements that sort of this whole thing was sort of poster child of cooperation between the various government agencies. This is at NASA Ames. This is the big hangar that they have dirigibles in and so forth. This is the U-2 getting ready to go out for launch. This is Mark Victor Gorenstein, who's the grad student who got his PhD off of this experiment. And you can see we had a cover over our thing all the way out to the runway. When they finally got out the end of the runway, they lined it up. We took this cover off so that it wouldn't have condensed. And you notice these things, when the thing runs down the runway, the wings get enough lift, they fall off, and people run behind in a truck and they pick them up. And this thing goes down like a bicycle and takes off, and when it takes off at an angle about like that, because it has to get from 0 altitude to 70,000 feet in a very short time. So it's a really impressive takeoff. It goes run down the runway, it's perfectly balanced, on 2 wheels, and then it goes whoosh, and it goes straight up like that. All you see is the tailpipe. And then it's up there, and you hear them they say, all right, we're getting ready to take data. We're going to be radio silent during all the time because we didn't want them to broadcast when we were taking data. And they'd sit up there for 4 hours, back and forth, following the plan that we had, and then come back, and our equipment would be in great shape, which was way better than my experience with what happens when you fly in balloons. And here is the data we got. You can make these measurements, and I could show you the pattern in the sky, but we measured various strips on the sky at different headings at different times of the year, so we covered the northern sky fairly well. And then if you look at what the temperature difference is between those patches as a function of angle to a direction that we pick out by best fitting and seeing the shape, we find that you get this nice cosine curve that fits fairly well, and you can fit to its amplitude, and you find that there were no other quadrupole or other things like that. There have been a few other measurements that seen variations on the sky, but they didn't have a well-defined direction the way we did, and they didn't have the fact that the quadrupole was much lower than the dipole and so forth. There were sort of hints there was stuff around there, but when you actually look at it, this was an experiment that first said, yes, there is a variation. It's a simple cosine variation going from hot in one direction to cold in the other direction, and everything else was much smaller than that. And so when you turn this into a best estimated map, this is what the map looked like in celestial coordinates. It was slightly hotter in this direction with error bars that are about 10 degrees. The result we think is best today is the hottest point is right about here. And this is the cold spot in the opposite direction. And we put the constellations on, which was a tactical mistake because astronomers don't think you're doing real astronomy if you put constellations on. And the other thing was this was a big surprise because, in fact, this is the wrong direction. The plane of the galaxy cuts across this map a different way. Everyone knew the galaxy was at rest. All the astronomers knew in those days the galaxies was at rest with respect to the rest of the universe. Otherwise, Hubble expansion wouldn't work. And they knew the galaxy was rotating, so you could predict exactly that the direction we're going should lie in the plane of the galaxy, and it should be in the direction we're going around. This is almost the opposite direction. It's 45 degrees off the other direction. And so that meant that though we thought we were moving at 3 out of 3 Kelvin, that is the 1,000th speed of light, the whole galaxy was moving at roughly twice that speed in the opposite direction, and astronomers really objected to that for a while. But eventually we came up with an explanation. So here's a little sketch that I made up for Kobe, but it works for the U2 too. Also. Just neglect the orbiting here, and imagine you're sitting above the sort of the Bay Area, and you're flying back and forth. You're on the Earth is rotating, the Earth is going around the Sun is going around the Milky Way, right? So you start adding velocities up in order to see this effect, because the end result is the sum of all the velocities to give you a Doppler effect. And then you realize the Andromeda galaxy and the Milky Way are orbiting each other, but it's not very much compared to the 200 kilometers per second we're going around the Sun, right? But then there are big clusters around us, the Hydra Centaurus supercluster, the Virgo supercluster. We should have a net velocity because we're gravitationally attracted there. But that was insufficient. You needed a huge object, a much bigger object, much further away, because this meant our galaxy's moving, Andromeda galaxy's moving, all 14 members of the local group are moving, and they're not being tidally pulled apart. They had to be, being pulled by almost uniform gradient, right, all across the whole cluster. You needed a very large object very far away in order to pull everything smoothly. It's just imagine you had a bag of feathers, a feather pedal, and you took the bag off and you just have the feathers sitting out there, and now you have to pull them somewhere, right? They're going to stretch out into a stream unless you have basically uniform acceleration across the whole group. And so the model we now have is the universe is full of great attractors on many different scales, but this got the name, at the time by astronomers, is this big object out here with the great attractor, the thing that's pulling us in the sky away from our Hubble destiny. Okay, and so this is the beginning of it. After this discovery was announced, and the Kobe discovery was announced somewhat later of the actual variations, the Smithsonian came and said, can we have your equipment? We'll put it in the museum because we're going to make a big display about measuring the fading afterglow of the Big Bang. That's what it says here. This is the fading afterglow of the Big Bang in front of this thing. So I happened to walk into the, going to Goddard and stuff like that. I went into the Smithsonian, and there you see your equipment in the museum, which is kind of, makes you feel a little older, right? not as old as I feel today, because I have stuff in more stuff in the museum. And here's the thing sitting behind this plastic case with a nice description of a differential microwave radiometer and the historical significance of this. And I pressed my clamor against the plastic and took this picture, and I thought, it's kind of funny they had to put the sign on here, the light goes in here. And then I realized I knew the light went in there, but the average public doesn't necessarily know. It's not obvious, it looks like a big mess. They also, even though they said they wouldn't change the equipment, they cleaned it up. They took a lot of the cables off so it looked prettier. But otherwise, it's the same instrument, but it's in the museum now. But at roughly the same time period began measurements of polarization, and it's only been in the last few years, the last 5 years, that polarization has actually been detected, and by the DAISY experiment and the cross polarization by the WMAP experiment. But there were two groups, our friends in Princeton, who started actually a year before us, although we didn't realize it yet, and Phil Lubin, who was a graduate student at the time, for his thesis, did a measurement at 1 centimeter of the polarization of the cosmic microwave background. And so this is Phil adjusting the electronics and me putting the calibrator into place, posing for the photographer. You'll notice I had red hair and a red beard at the time, and it was long hair because it was San Francisco and so forth. And here's Peter Nanos, and this is a more recent picture of him. He was a young grad student at Princeton working with Dave Wilkinson. After he finished his thesis, he went into the Navy, and he eventually became vice admiral. And after he retired from the Navy, he became the head of Los Alamos Laboratory, although only for a couple of years, and then he left. And so it tells you, you don't, just because you start in CMB doesn't mean you have to spend your career in CMB. You can do other things, right? And here is the second generation. This is Philip Melisse, who did for his thesis a 3 centimeter wavelength for the polarization, and we set tight limits at the time and didn't get there. And this is Hal Doherty, one of the people that I inherited from Louis Alvarez, a wonderful designer and mechanical mater, and he was responsible for a lot of the beautiful equipment we had, including the DMR you saw before. And then we thought we should, as soon as Phil graduated, we thought we should move in to improve measurements of the anisotropy. So we thought we'd come up with a balloon gondola that had a cooled receiver, a liquid helium cooled receiver, that looked out at the sky, and we chopped back and forth the two beams on the sky, and then rotate the gondola in order to exchange it and fly it on a balloon. So here's the payload, there's a ladder, and then a parachute, and then the balloon above it. And here's what the receiver, the part that was going to be cool, looked like. You can see the sort of beautiful precision engineering and the mounts that it gets put on to make it sort of uniform. You can see that, again, we're using the corrugated horns, but now for scale to 3 millimeters instead of 1 centimeter. And here's what the equipment looks like inside the liquid helium dewar. It's upside down. This is where the horn looks out, and we put a window on it because the horn gets cold. We want everything smooth. You can see how clean and shiny you had to make everything just to keep the radiation loads low. And here are the two students who got their PhDs on it, present day pictures, so they look a little older than the students. Jerry Epstein got his PhD on the Northern Hemisphere flight. Tirso Villela got his PhD from the flights we did in Brazil. And he worked for the Office of Technology Assessment now and works now on science policy and the government. And so here's what the receiver, the whole system looked like: the liquid helium dewar, absolute pressure relief valves, the ground shield. The horn is pointing out here. Here's the chopper, and it's polished aluminum, so you can see the mirror image of it. So you can see how the beam works. Here's the thing set in we designed it to fly at a 45-degree angle, so the helium can stay level that way. The horn is pointing out 45 degrees this way. If this chopper rotates around, it reflects the beam to look at 45 degrees the other way. And one of the things we started doing is developing calibrators that get put in the beam. So here's the calibrator stowed. Here's the calibrator in the up position. We send a command or have it on timer. It would come up, be there for rotation, and come back down, and we'll continue taking data. So this is a way that we had something was in the far field, whose size was carefully designed and whose reflectivity was carefully designed, whose temperature we monitored, so we knew what the signal level was. Okay. Now at the same time, the Princeton group also realized in order to get sensitivity they had to good co-receivers, and so we came together at the balloon flying facility, and here's how they were beginning to assemble what was going to be their balloon gondola. We actually shared the first payload ride up, and then we built our own apparatus after that. And you can see they have two horns that are pointing to the part of the sky, and then waveguides that go down into a cooled region where the detectors themselves were cooled. Here's what the thing looks like assembled. Right? This is Princeton t-shirt, but with a jacket on, so he looks cool. Right? This is Peter Salson, the grad student who was working at that time. And here is the fully assembled equipment. And their approach to getting the side lobes low enough to reject the Earth was to use curved metal surfaces. Right? And the radiation doesn't like to keep curving, so the electric field moves away, and therefore the far side lobes were low. This is something that we ended up using on FireAss. But the way they got these curved surfaces, they went to the music store and bought musical instruments and cut the bells off. So these are, the music of the sphere being broadcast in instead of out, but in microwaves instead of sound. But you can see how the whole apparatus looked when it was sort of assembled. And this is a picture that I took of Peter Salson and Dave. I think this is Peter and Dave. When we were getting ready for flight, you can see the bells from their musical instruments on one side. Our equipment was just in the same foam, on the same gondola, inside the same screen. It's on a ladder. It rotates around when you get up in altitude, and this is how the whole thing looks. These are the people whose job it was to do balloon launches in those days, assembling the antennas and the last-minute stuff. Here's a picture of what the gondola looked like when it was on its way up. Here's the balloon with the helium in the top of it. As it goes to higher altitude, the helium expands, and eventually this whole becomes round. This is the parachute, and then this is the ladder. And because the balloon gets so big, you wanted a long ladder for two reasons. One, to get far away from the balloon, so it wasn't near field view. But second of all, so you had something to drive against. If you start rotating and you have just a single wire, it'll twist all up, and then it'll untwist, and it gets to be a mess. But if you have a ladder, it works out reasonably well. And this is the map we got after 3 balloon flights, 2 Northern Hemisphere flights and 1 Southern Hemisphere flights. You can ask how come we only had 3 flights, and the answer is our gondola got lost in the jungle. It actually never made it to the ground for a year and a half. It was hanging from the trees in the jungle, and it was hanging about this high. The bottom of the gondola was about this high in the jungle. And it wasn't found for over a year. We posted rewards, a bunch of stuff. We gave up and tried to analyze with the meager data we had from the telemetry. And then about a year and a half afterwards, we got a phone call that somebody had been in town, in this small town, trying to sell parts. And this guy turned out to be, he was a palm heart poacher. That is, people like to have palm hearts and salad. This guy would go into the jungle, and which was forbidden because it was a park in Brazil, go into the jungle and kill young palm trees and steal their hearts and sell them to rich, Europeans and Americans for their salads. And he happened to come across the gamma in the jungle, and he saw it, and and eventually he was persuaded to take the reward, and we got our gondola back, although missing a few pieces that he'd taken off, and covered with mold and mildew and so forth, but including the data tape. But the computer people were able to take this moldy data tape and somehow reconstruct the data so that we got our data and we got to make this map, but we didn't fly one more time to fill up the map. But what you can see is a real map here, no longer a fit. This is the actual data just loaded in each pixel. You can see the region where it's warmer in the direction we're going, and blue in the direction it's cooler, and you do the fit and you find very precisely. And at this time, there were actually controversies about whether there was detected a next level, and this map was able to show that the two claims that there was a quadrupole were incorrect and that we needed to go on. This is one of the first computers that's a large integrated chip rather than in the discrete transistors. That's how old this is. You can tell there's a teletype here and a terminal that looks a little old. I mean, there was a modern terminal those days when I took this picture. And this is the other thing that's going on, that we were also making spectrum measurements. And so we're back at White Mountain. Remember the first picture of Dave Wilkinson? We're back at almost the same site. Well, the picture would have been just a little more to the right here. This is the Milan group headed by Giorgio Cerrone, making the longest wavelength measurement. The Bologna group, this is Reno Mandalese, who was the head of it, making measurements at the next wavelength. Then we had a liquid helium coal load buried in a hole in the ground. We built this railroad system so we could roll our carts back and forth. These are 3 radiometers from Berkeley, and this is the Havre group measuring, and Bruce Butcher's group measuring the atmosphere, monitoring the atmosphere during this whole time. So we put together this huge collaboration to end up making measurements essentially at 5 frequencies on the long wavelengths, and we had to build scale receivers. You'll notice they're all corrugated horns. It's all, and it's a pleasant environment to be in. And so here's the people that were there at the first time, and then we went back several times and added people. But you will notice that for some of these, this is their first cosmic microwave background experiment. Reno Mandalese, who's one of the Planck PIs, Marco Bersinelli, who's one of the deputy Planck PIs, and a number of people, Alan Koga, Steve Levin, some of the people that worked on WMAP. This was their first experiment learning how to do measurements of CMB. So there is not only the measurements, but there is Michel Limon. There were people who then went on to do the next generation and the next generation experiments. And in those days, things were really crude. We did things manually. We had a liquid helium load, but if you expose liquid helium to room temperature, there's a very large radiation load, and the helium will boil. So we had undergraduates who got to help in research. This is Alan Benner. His job was to keep the shutter closed, that is, keep a highly reflecting, low emissivity surface facing the helium, and only open it when we were taking data, that is, looking down, taking data, and close it again afterwards. And so it's almost so manual intensive. This is Scott Friedman, who got his PhD thesis from measuring the 3 centimeter temperature. We're looking down in the coal load at this picture, although we're not actually because the shutter is closed. And he and I would sit on the rails or stand, and we'd flip it around either to look up or look down. The second horn, so this is differential, looks off this reflector and looks straight up. It's actually a 45-degree angle. It just looks funny there. So the operations were extremely manual, and we just took data with that LSI computer. That's how crude things were. And we also went to another wonderful site, the South Pole. So this is the Italians and the Italian flag, and the Americans the American flag, and one person off taking the picture, showing at the geographic pole. We didn't go to the ceremonial pole for this. We had to go to the real pole, which is another 100 meters away, because the ice is moving slowly. And I had to get my picture taken next to the pole. You can tell it's me because my name's on that's how when you came in to eat and you took your parka off, you had to know which parka was yours, so they had your name on it, right? So, and this is what our site looked like. You'll notice the horizon, right? I mean, when the wind blew, you couldn't see anything. It was just like you're in the middle of nowhere. But it's just like being a really big ice cube. That's what the situation. So we cut a big hole in the ice, which isn't really solid ice. It's just kind of a lot of frost put together. We cut a big hole in the ice for the liquid helium door and a big pit for doing atmospheric measurements. And we waited for a calm, sunny day, to take our hats off so you could see who we were. And so the names of the people are down here. But this is sort of the crew. We had the South Pole, and there's a receiver here in the background with the shield built around it. But just to show you an up close, this is Marco Bersinelli before his, and Mark Benzioni, before their beards were white, just like my beards weren't white then. But in the pictures, they're white because your breath froze on your beard, right? Now Marco's beard is also getting to be not so, not so black as it used to be. And you can see again, we had the corrugation design. They weren't round, but they're still the corrugated horn kind of design in order to get the side lobes. And we had one other thing that we did for fun. Since we were down there for Christmas, we had to send back a Christmas card. So you'll notice this is a person, and in fact, all those are people. And so it's a real organizational skill to get people to lie still on minus 40 degrees C ice while you climb a large ladder, arrange them and then climb a large ladder. This was the clean air tower. There's the sample where the cleanest air in the world is. There's this large tower on the upwind side of the station so that you could climb up high and take a photograph right now. So anyway, Merry Christmas. But this is the beginning of, motivation of people, right? Well, it's been before. This is a real example of motivating people. But actually, if you notice, one of the S's is better than the other. People aren't all completely motivated, but we'll see. At the same time, Paul Richards and Dave Woody continued on the project that John Mather started for his thesis, and they eventually got a good measurement using this apparatus which flew in a balloon. And here is Paul, took his picture next to the equipment before they sent it to the Smithsonian. It's also in the Smithsonian from the same display. And here's what they did. Here's pictures of them at that time. When I showed this picture, Paul Richards said, "There is no way that I ever had long hair and looked so young." And I said, well, that's when the picture was taken. That's what you look like. And this is Dave Woody, who was always kind of shaggy, and so forth. And they measured with the Fourier transform spectrometer a spectrum that looks sort of like this. And the atmospheric spectrum looks like this when you subtract the difference between the load and so forth. You see there are lots of atmospheric lines, and the cosmic microwave background is in here. You have to subtract away a model of the atmosphere, and you get this residual spectrum, and when you add them together, you get this shape. And so it doesn't look very impressive until you plot it in terms of frequency versus flux, and you see the predicted blackbody curve, the best fit blackbody curve in here, and their measurements, and then the measurements we were making at long wavelength are down in this region. You can see that it's pretty good, although it's 2.96. Okay, so 3 Kelvin's pretty good, except in the end we find it's closer to 2.72. But this was the progress that was made, and there were things that were learned from this experiment were then turned around in order to design the PHI-RAS instrument much better. So the PHI-RAS instrument, here are the results. Here are the Woody and Rich results. Here, these 5 points are the points from our collaboration. This is the original Pinson and Wilson point, and these are the other measurements that have been made over the years, including some where you look at very distant clouds of gas and you find them shielded away from stars so that only the microwave background is heating them up, and you can measure the temperature of the molecules. Right? So there are different techniques for doing that, and you can see what it looks like. We finally were at a point where we were convinced that it really was a blackbody radiation, and this was roughly in 1978 that the evidence was fairly strong. This particular plot is from like 1984. 1978 is when Pinson and Wilson got their Nobel Prize, because then it was obvious that it was a relic radiation from the Big Bang. But there were still some doubting Thomases, and so it's why it was important that the PHI-RAS instrument be designed. The PHI-RAS instrument was designed to be extremely symmetric and to do differences. And so it's a Michelson interferometer, but it has 2 inputs. There's one input here that comes in this way and goes either that way or this way, and another input that comes in and either goes this way or that way, so that they're exactly symmetric. You try and design the thing to be as completely symmetric as possible. You either get a signal from the sky or from an absolute well-known black body that you can move into the beam, so that you place the sky with the beam. And then you have an internal reference black body that you're comparing with, whose temperature you can adjust very accurately by little heaters that on the sand that goes to it. And then when you do the motion of you move these 2 mirrors very carefully. When you do the motion of the mirrors, the signals are recombined. One set of signal goes to detectors here, the other set goes to detectors on the other side. But if you do a smooth motion of the mirrors, the answer you get is the Fourier transform of the spectrum, right? Just of the movement. So the physical distance you move measures the wavelength precisely in an absolute way. So you have an independent kind of a measurement that way. But what you do is once you get in orbit and the lid is blown off of the door, you keep doing interferograms and you keep adjusting this temperature till you get a null. And if you get a perfect null, the gain of the system doesn't matter. A lot of the secondary effects don't matter. Once you've got an interferogram that's a null, that is, if it is a null, and there's no variations across it, then you know you've measured the temperature and you've measured the spectrum very precisely. If there's slight variations, then your gain is sort of second order. And so as soon as we had the door open, and after we waited for the water vapor and other things to evaporate, then the lid to the bluer was removed, and then observations started. And with only 9 minutes worth of data, the spectrum came out to look like this. And this is with 400 times error bars, which is hard to understand. So I'll show you some close-ups to see what it is. Here's what the FIRS instrument looked like. It has that sort of bell-shaped horn that you need in order to look over a very large bandwidth. You can't make corrugations that cover a couple of octaves. So you have to use the Princeton approach in this. And here's the calibrator. There's a shower cap over this and there's a cap over that to protect them to launch. But that's basically how it is. And this is the shape that Planck predicts. And then the data bars are on that. And there is an absolute calibration here, so you're not depending on just the differences. You actually have some absolute information in this. And so I'm going to show you the results of years of hard work in terms of the spectrum and in terms of the temperature measurements. So here's the spectrum blown up. Here is the FIRAS and the University of British Columbia experiment called COBRA. It's a rocket launch experiment, happened about the same time. Here are these, in green are these ground-based measurements, red, Pitzius and Wilson. And then after that, with a series of balloon experiments trying to make improvements in this little gap where the atmosphere bothers you too much from the ground in order to make a precise measurement. And you can see the shape is very impressive. This is a log plot, so 90-something% of the energy falls in this region. You can see how precise the measurements were. And if you go to temperature, you can start seeing the deviations a little bit. Here's the temperature of 2.72, I think. I took it off when I redid this. Here is the university, this sort of curve wiggling up and down is the rocket experiment from the University of British Columbia. This red line on here is the FIRS measurement. And if you have to look really close to see that it actually goes slightly off the dotted line, which would be a constant temperature, and that's within the error bars. I mean, it's an incredibly precise measurement. And I'm sort of embarrassed by our ground-based measurements. You know, we barely are, statistically significant with it, right? Because the error bars now look big compared to the FIRS, right? But still, it turns out to be important because if there were deviations in this area, that would tell you something about the nature of the universe during the early time. In order to establish the radiation be this uniform, it has to happen within the first year after the Big Bang. If you start having distortions after that, there's insufficient number of scatterings and reallocations in order to reestablish it. So this is telling you, what was happening in the universe one year after the Big Bang and later. Okay? And so it's fairly impressive kind of step forward. And this is part of the thing that went on that I sort of used to joke about Joe Silk having two opposing ideas in his head, but that's the example we use, that when we were looking at it after he gave that first talk, you have to either prove that the 3D background radiation is not from the Big Bang, or you have to say it is from the Big Bang and measure it precisely and say, what can I learn about the universe? So those are two opposing ideas. You have to be skeptical on one side, and you have to be believing on the other side. It's like going to a movie and suspending your disbelief to see if the plot makes sense, right? But at some point you have to say. And so with the FIRAS measurement and a couple of the other supporting measurements, you're really convinced that you know that this radiation came from the Big Bang, and it's a tool that's sufficiently strong and calibrated that you can use it to understand about the universe. So here was the original artist sketch for what the COBE satellite was supposed to look like. Inside there was a dewar for liquid helium. It had the FIRAS measurement and the diffuse infrared background measurement to look for the first stars looks at the light from the first stars. There's indications we found it, and Jean-Luc Pouget was one of the people who used that data to do it. And then there were the 4 differential microwave radiometers around the outside. And we were directed in the early parts of the project in the late 70s, early 80s, to move it to be flying on the shuttle. So these are the things that fit in the sides of the shuttle bay. It's all this big structure and a hydrazine to get up to a high orbit. And we had reached, by January '96, when the Challenger blew up. The Challenger was the shuttle we were scheduled to fly upon. Not at that time, but in later flight. when it blew up, and we were left without a way to get into space. And so at the time, I had friends in France, and so I came over and talked to CNRS about possibly getting a rocket. And we talked to some of our Russian colleagues about possibly collaborating with them because they were trying to launch the Relic series and make the measurements. And we said, we have the experiment almost ready, but we have no way to get to space. But when NASA heard that I was talking to people like that, they got all upset and they said, look, we're a space agency, right? Our job is to put stuff in space. And if you guys really want to fly so bad, we'll let you be the first to go into space again. We'll make you a Tiger team, and you can be the first new mission into space. And they went around and they discontinued making Delta rockets. They found the spare parts laying in a warehouse. Some of them rusted, and they said, okay, we have enough spare parts to put together a Delta, right? We'll let you guys have that Delta, right? And of course we were worried some of them were rusted and so forth. But it's better than nothing. And since they said it was not possible for us to fly with somebody else, it would be too embarrassing for them to be shut down for 2 years and we're flying. We had to go somewhere else. So they let us form a Tiger team to redo it. We had to lose half our mass, and we had to do a lot of other things to get back into Delta configuration because we've been designing for the shuttle configuration for a long time. And so and one of the things we had to do was we said, well, we already have the door, we already have the instruments to go in the door. We can't change that. But we have to be able to fold it up and fit inside of the shroud. We have to do it. So we had to redesign my instrument completely to make them thinner and flatter to fit around the door, so that the folded up shield would be able to fold up and then unfold. And so I also knew from our measurements that we were in danger of not being able to detect the anisotropy because the limits kept getting lower, and just the kind of things we were doing was saying we needed more sensitivity. So I said, look, we've learned how to make cool receivers that are stable and work. Can we not, while we're taking these apart, turn these into cool receivers? And they said, well, come and make us a presentation and we'll talk about it. And there was some talk going around that this is just another scientist who sees a little window and he wants to make his instrument better, right? Because that's going on. And so I made the presentation, and they were kind of convinced, but they still wanted to test it. And they said, we're willing to do it. We're willing to let you cool 2 of them if you give up 1 of the 4 and you leave the other one as a warm receiver the way you originally planned it. And I thought about it for a short while, and we decided to do it. And so suddenly we went from 4 DMRs to 3 DMRs. We threw away the lowest frequency DMR and said, which was to guard us against having signal from the galaxy and so forth. And I chose to cool the 2 highest frequency ones because that's where I thought the galactic backgrounds were the least, even though it was harder to make those work than the lower frequency ones. We did it. And so originally from 1976 up to 1985, we were just these few people, right? The 3 principal investigators plus other members of the working group. These were people selected from the 3 proposals that went in to propose to this kind of measurements at the time of the announcement. Later on, we added 12 additional scientists, and after that, we added, by the time we got into the data analysis phase, a bunch more scientists, but by that point, NASA wasn't officially recognizing them, so they're not officially designated scientists, but they were critical, and their names were on the papers. Here's a picture, whoops. Here's a picture of the science team minus Ellie Dweck as of the late 80s at one of the meetings we had there. So here's Dave Wilkinson, here's Ray Weiss, who was our chair, here's John Mather, Ned Wright, myself, all the tall guys in the back row, the shorter guys in the front row. What? But, a nice fall day in terms of what's going on. And here's some of the people that worked on the hardware. A lot of engineers and a lot of technicians worked on the hardware. And at the beginning, I got to work with 2 of the more senior engineers because there weren't that many engineers doing microwave stuff. This is Roger Ratliff, whose job it was to take the stuff we'd done on mountaintops and balloons and turn it into spaceflight-worthy kind of hardware. So here he's holding the mechanical design for what the corrugated horn antennas would look like at 1 centimeter. And then John Marshak's job was to take whatever we made and test it really thoroughly and calibrate it and make sure it was meeting the specifications. And so these 2 guys were core guys for a long time. I spent a lot of time working with them. And then finally, when we got approval to go ahead, Goddard had been under hiring freeze for a very long time, and they got to say that they were going to build it at Goddard, so they got to hire young engineers. And so we hired these young engineers, and she had just graduated from college, right? She went from the University of Miguez in Puerto Rico. This is Maria Lecha. These guys had been out for a year. He'd been out for 2 years. He'd been out for a year. These guys were brand new hires right out of college. And first thing I had to do was sort of motivate them about, well, how exciting the science was going to be. And I gave each one responsibility. Originally, his responsibility was a 9 millimeter, 30 gigahertz, hers the 53, his the 90 gigahertz, and his the 23, but he got killed. The 23 got killed. So, but we now had to build a test chamber that would test the cool receiver, so he got put in charge of the test chamber, also in charge of everybody, because he wanted to be that way. And this guy was in charge of making sure the test procedures and results came out okay. And these kids, right, they would come in at 2 o'clock in the morning when something went wrong. They would have to go and deal with senior managers and engineers to get parts for their receiver. They each took responsibility for one of the receivers. It's a pretty impressive kind of thing, and they did a great job. And then at the end of the hardware phase, then new people came in to start doing the software and so forth, but they were outstanding. And this is a picture of Kobe from the last time that I saw it up close. This is in the Western Test Range, which is at Vandenberg in the US. You can now see the 9 millimeter, the 3 millimeter, and the 5.6 millimeters on the other side. Here's the door, here's the lid on the door that gets thrown away after you've been in orbit for a week. And this is the shield that gets deployed. My job at this particular time was to go down and see the shield deploy and then go around and inspect that there weren't cracks and that all the joints were right and everything was okay, then sign off on it for it scientifically. So I got to dress up in one of these bunny suits and go around on my hands and knees looking top to bottom and then turning the lights out and running up and down with a drop light to try and make sure everything was tight. So I have a 2.5-hour video that's so boring that you can't stand to look at it. But that's the time, the last time that I saw it. Although it turned out I saw Kobe by eye once it was orbiting, because we orbitate on the terminator, that is the day-night line, so that Kobe is always in the sunlight and it's rotating, but it's tipped back slightly, so the sun doesn't shine inside here. It only shines on the outside and on the solar cells, which would be below here. And they're actually hidden from your view, but they're down below on the first floor. And that as it rotates around, it's in the sunlight when you can be in the dark, and you look up and you see what looks like a twinkling star coming up over the horizon north and passing overhead. And it was at the beginning synchronized to exactly 14 orbits a day. So it always came over at the same time every day, and you could go out as the sun set and see it by your own eye. So this is what it looked like on orbit, except it just looked like a speckly spark. And the solar cells deployed and the equipment in there, except the sun's not shining in here, and it took a week before the lid was blown off. Okay, so after this, we were able to make maps. So here is now the dipole map in galactic coordinates instead of celestial coordinates. This is the warm spot and the cold spot. Here's the galactic plane. You're looking down the spiral arm one way, you're looking down the spiral arm the other way. We're in the spiral arm. So if you look in opposite directions, you see down the spiral arm. The galactic center is here. You would expect that the hot spot would be in this direction, 90 degrees to the galactic center, because we're orbiting around if you're an astronomer, but instead it's in that direction, but now you can see it very clearly. The signal noise is very high compared to the original maps that we were making. And then if you subtract away that Doppler effect and you look out here, you see now the scale blown up about a factor of 100. You see the galaxy saturating across here, but off the plane you start seeing these areas that are the large blue areas with lots of blue spots in it, and large warm areas with lots of red and green spots in it, blue areas all associated, and red areas. And that's an indication, or with the galaxy massed out, you see this kind of an effect. That's an indication you're seeing structure on several scales. If you have a very long wavelength variation across the sky, when it's peaked and you have lots of small peaks going up and down on it, right? So it's like fleas on a dog. The peaks all cluster together. The pluses all show up. The ones that go back towards the mean don't show up so much. Likewise, if you're in the low part and you see the negative going peaks. And so if you sort of practice and train yourself, you can see this, although it's nicer when the galaxy's not in there to see it. We'll have a map of that later on. And that shows that things were roughly equal variations on all scales. And then we were doing a series of balloon experiments, Maxima and Boomerang. And when you look at them, the moon is roughly a little larger than this red spot. When you look at them, you see variations that pick out a particular scale. There's a characteristic scale on both of these maps, which is around 1 degree. And that is the beginning of what you start to expect if you excited the universe roughly equal amplitude variations at the beginning, As time goes on, things can move around, but they move around at speeds a little less than the speed of light. And things that are less than the speed of light will then pick out scales that can show up. All right, so here are the people that were involved in Maxima and Boomerang. Some of my colleagues, these people from the Maxima. These people were also the beginners of the Boomerang experiment. And then later Andrew Lang moved to Caltech, and slowly the teams diverged, but their origin was the same. And here's what the spectrum looked like shortly before WMAP started to get its results. Right? So here are the fluctuations versus either the Zonner polynomial number, since we're in France, or angular scale, large angular scale, 90 degrees across the sky, 50 degrees, 10 degrees across the sky. This is the measurements from COBE. This is the measurement from the balloons and from the DAISY experiment on the ground, but mostly the balloons, starting to pick out a particular angular scale that's just about 1 degree on the sky. Okay. And this is not surprising because this turns out to be the angular scale size that if you set off a sound flash in the early universe, its size would be roughly 1 degree on the sky at the time you observe it with the microwave background radiation. And then harmonics of that will also show up, and we'll talk about that in a second. So the first thing that happened when we saw that map is I told my grad students and postdoc, the universe is flat. They said, that can't be right. We got to do the analysis and see what's going on. I said, well, I've seen enough simulations that I know that we're roughly in the right ballpark. And so we did the full analysis, and the answer turned out to be that way. So we know that the geometry has, in large scale, because of the fact the universe is pretty uniform, these variations only a part in 100,000, we know the large scale geometry has pretty much constant curvature, and there's only small variations in the curvature. So the only spaces that allow that are spherically curved spaces, flat spaces, and saddle-shaped spaces, open spaces. And in those cases, in this case, parallel lines stay parallel and never converge together. The sum of angles in a triangle is 180 degrees, and everything is fine. If you have a space that's concave like a sphere, you start on the equator, go up, longitude lines, they converge at the North Pole. So parallel lines that start out parallel converge. So the sum of the angles in a triangle is greater than 180 degrees. And the opposite is true in the negative curve space, the saddle shape or a funnel shaped space. And so you can use this information and the fact that you know what the speed of sound is in the early universe to measure the geometrical aspect of the universe. And you can do it, so here's the moon for scale. I put it in this particular picture. You can look at the actual data from Maxima and Boomerang and see the scales. You can do simulations of what would happen if the universe were closed, if it were flat, if it were open, for the given level of fluctuations, the prediction of what the sound horizon should look like. And it's easy to pick out that it's close to flat if you've done the simulations and you put them up next to the data. But you can also do the Fourier transforms of the data or the spherical harmonic transforms of the data and look to see where the peak is, and you see the same kind of thing. And so we had a very good idea, and there were press releases and big stories and hoopla made that the universe was flat. And WMAP continues on what COBE did. So this is a map as made by COBE with 4 years of data and with the best estimate of the galaxies subtracted. Here is the same map made by WMAP with this first year of data. And you will notice the similarities. The difference is you got an order of magnitude more angular sensitivity, so you can see much finer detail. So I have a plot somewhere where I couldn't find it that shows what the world would look like with COBE resolution, and you can see the 5 continents, right? But with WMAP, you can find Madagascar and Paris. Well, not Paris, but France anyway, or Italy. But with COBE, you wouldn't have been able to see the difference between Italy and Europe, right? I mean, it's you wouldn't see that difference. But if you look, here's the large positive going region, the same large positive going region, the cool region, the same cool region. When you do a careful comparison of this, you look on the same angular resolution, you see these maps are essentially identical, right? So which means either the COBE team and the WMAP team made exactly the same mistake, or they got exactly the same sky they're looking at. And we know that the WMAP team was really careful, right, Olivier? And so, we believe that both teams were correct, and they got a good measurement of what the universe looks like. And so with the WMAP data and some additional experiments that come on, you can now do the spherical harmonic analysis and look and see what scales. Now you do it on a log scale, so the COBE results are way buried down in here. There's this variation here caused by the sample variance, caused by the fact that there are not that many waves that can fit in that are 90 degrees across the sky, so you have a very limited number of samples there. But as you go to higher and higher waves, you can get more and more different ones in there. So your error bar goes down. So this is a measure of what your sample variance from the fact you can only see a limited part of the universe. And you can see this first peak showing up extremely well and very precisely in terms of multiple moment or angle on the sky. So then you now know much better, more accurately, how flat the universe is, and it's still very flat. And you can see the second peak showing up very well now, where there was only a hint of it before, and then some indication of a third peak. And here's the theoretical model, the best fit theoretical model drawn there, where you see a fourth and fifth peak, right? And so that was the status as a couple of years ago. Then another new experiment has come along that's made a lot of progress, the arc-minute bolometer array, again at the South Pole. Why do we love them so much? Well, it's water vapor. You go where there's a little water vapor, you get a better measurement. So this is an experiment run by John Rule, co-led by John Rule and Bill Holzapfel. Here's two pictures of them. And here's what the receiver array looks like. It's a bunch of bolometers with feed horns, very similar to the same thing that the HFI for Planck will do. So very similar technology. It's all in a very cooled, is liquid helium, but with additional refrigerators in it to get to extremely low temperature for high sensitivity. And then it's all put inside of a dewar. It's then looks to a mirror, and then to this primary mirror. The whole thing is at the South Pole, this huge array like this. It actually quit taking data in 2005, and they're just analyzing the data now. But if you take the 3-year WMAP data and the ACBAR data that was released about 3 weeks ago, this is the spectrum you get. These blue points are the 3 years of WMAP data showing up here. Peak 1, peak 2, peak 3, peak 4, 5, 6, 7. I might have miscounted one, but you can, in principle, with the quality of the data we now have, you should be able to see 7 peaks, right? You should be able to see the fundamental and the harmonics of the universe showing up extremely well, and also the boomerang data is put in there just to cover in this region. But in fact, you can see that as the data are analyzed, there could be 4 times as much data. That means the error bars from ACBAR in principle could go down a factor of 3 or 4, because this is a power spectrum, not an amplitude spectrum. So in principle, we're going to have a fairly precise measurement here. WMAP continues to take data. It will improve some too, although not by as big a factor. We have a fairly impressive measurement, and then we expect Planck to come along and improve it even further. And so that's, as I was saying, we have a future. Planck is scheduled for launch sometime in 2008. Here's sort of an artist drawing. Here's a sort of more fanciful artist drawing. The issue here is this is the mission that is primarily led by ESA. It's at least 80% European. And then there's a strong North America contingent. And NASA is funding a lot of it, but also Canada is. And this is sort of the artist conception, you know, against the ripples in the space-time, the fabric of space-time or something in the background. And we expect them to come along, and we expect an improvement to happen. So here's the map of the sky, the globe map of the sky, the new beach ball. Here's the resolution you get from COBE. It's very coarse, but we were able to actually see there was something there. Here's the resolution from WMAP at this highest frequency channel. But if you want to do really careful cosmology, you have to make sure you remove the background. The longer wavelengths have poorer resolution, so when you merge it together, you get a slightly poorer map. This is a cleaner map, but poorer resolution. With Planck, you should be able to get even higher angular resolution because it uses the bolometers and therefore higher frequencies and therefore has more angular resolution for the roughly the same size mirror. And you expect to be this continuing improvement in terms of that and more frequencies, so that you hope that we'll be able to continue the progress that we've been making understanding cosmology. And as I didn't overrun too much, I hope. As I promised, I was going to tell you back about the Sunyaev-Zeldovich effect. There have been a whole series of experiments about the Sunyaev-Zeldovich effect since Rich Miller and I did the sort of tried to do a pioneering observation and failed to detect the phenomenon. There have been slowly over the years the development of this and improvements and understanding better, but now we're getting into the stage where there's going to be large-scale production. So this is the Atacama Pathfinder experiment. This is the first telescope of a set of telescopes that will be an interferometer array in the Atacama Desert. This is the one, and a quarter of its time is dedicated to looking at the Sunyaev-Zeldovich effect. And the receiver, which was built by a group led by Adrian Lee from Berkeley. You saw his picture earlier. Here's the receiver. You'll notice one pi wedge is missing, but this is a whole array of bolometers and feeds in order to be able to take the image and so forth. And this, of course, is cooled and down to below liquid helium temperatures and put in this thing. And it has, last year began with engineering and first observation data. Now it will have the full array. You'll notice it's missing one right now. But essentially it's put together and it's starting to take data and expected to get science at this time. At the meantime, the second generation actually has made so much progress that it's catching up with the first generation. The South Pole Telescope, here it is set up in the United States, being ready to test it and being ready to ship to South America. Here's a human for scale. You can see in order to do the arc-minute resolution that you need to see clusters of galaxies, you need a big dish. And you can see the site where it's being assembled even as we speak in this room right now. This is the season in Antarctica when you go to the South Pole, because it's summertime there. It's only minus 20 degrees C, right? It's not so well about this time of the year. So it gets about that warm. So it's being assembled at the South Pole. Here's the base for the telescope where this is being put, and the pieces are actually being assembled now. And they hope to start taking observations in February. And you'll notice this pie-shaped piece, the one that's missing from the other receiver, the exact same technology, the exact same people are building the array for both telescopes, and so it's not an accident. This is a picture of BICEPT on the other end of the building. This is a polarization experiment that's starting to be in operation at the South Pole. So there's lots of ongoing experiments, lots of new data coming in. So the future looks pretty exciting. So we have this beautiful model of current cosmology where we have inflation. We have the cosmic microwave background giving us an embryo picture of the universe. Then we have the dark ages where the matter is released, but it hasn't had time to eventually form to stars and the galaxies and so forth. So eventually the stars form and the light turns on and we begin processing the elements and making things the way it looks today. And we have this surprise at the end that the universe is again starting to accelerate its expansion instead of continuing to slow down the way it did over this huge phase where structure forms. So structure formation is beginning to shut off, and that the tearing apart of the universe is beginning again. So that's one of the things we want to study. But this is just a reminder of how you can tell the universe is flat open or closed. You can use this technique and use the fact that depending on the constituents of the universe, you get different relative peak heights and harmonics and so forth. And so you can learn and start studying the properties of the universe, and we have fairly precise measurements. I don't remember if this is the first year or the 3 years of WMAP data, but it doesn't include the Akbar data in it yet. The kind of thing you can get is you measure the expansion rate. You can measure the total density parameter. That is, 1 would be flat in this measurement, and you can see we're very close to 1. That matter makes up about 25% of the universe. That the baryons make about 4.4% of the universe. Dark matter makes about 70% of the universe, with error bars that are 4%, 10%, and these kind of numbers. And you start going down this list of things that we know about the universe in aggregate, like its waist size and its, whatever. You see we're entering the regime now where we're knowing things to roughly the 5% level. We're hoping when these new results are coming in and Planck is working, we're getting down to about the 1% level. And I always tell my students, it's science when you can calculate it. We're getting to the point in the universe where we can calculate it. And now we want to understand it more deeply, but getting to that point where we can calculate it, and that's what we do. But there are mysteries like the accelerating universe. So one of the reasons I'm here in France is to talk to the scientists, but also to have the discussions between CNRS and the Department of Energy about having a mission to explore the accelerating universe and dark energy. And we're hoping that there will be a joint mission put forth by the United States and France, perhaps with other collaborators, to study this dark energy so we can understand what's the ultimate fate of the universe and what's this 70% of the universe that we can just give a name to, but we don't know what's really going on. Okay, so I am done, finally.
Thank you very much, George, for this very beautiful and instructive lecture. And we have enough time for questions, comments, reactions. From scientists or from journalists.
Maybe they're all tired. Maybe they all want to drink.
Sí, synthesization idea was put forward in 1980-81, Casanas, Moose, etc.
Right.
People today got the first estimations about the CND anisotropy. So there was predictions about 10 to the minus 4, 10 to the minus 5.
Right. Somewhere I have an old view graph, and I really mean view graph, piece of plastic with stuff on, that shows the theoretical predictions versus time and the observational limits versus time, and they crisscross each other, right? So the problem is, the theories have credibility or not, and the answer is, well, they always have a reason, right? But they had to invent dark matter, they had to invent, if you didn't have dark matter, the fluctuations would be higher. So in the end, nature decides, right?
Since these predictions were around, when you made the design of copy, of the EMS or copy, did you consider these things? Were these things around?
There were, that's what I was saying, there were predictions around, they were wrong. They were a factor of 30 too optimistic at the time we began the first proposals, and the theories only got to the correct answer and the lower limit about a year before we presented our data. I mean, the theorists were behind the curve, and they're definitely in cosmology now. Even though their theorists are acting very rapidly, they're still behind the curve of combining all the data. Nobody has actually done a global fit that you can be confident in. People do global fits, but there's just too much data coming in and too much to understand right now. We're in a situation where for 60, 70 years, the theorists dominated cosmology, and there were speculations because they had no constraints. Now they have constraints coming in faster than they can do it. Sometimes theories that are put forward are already wrong, but they didn't check that piece of data to see it's right. Now, the main idea of the standard model of the Big Bang seems to be accurate and not ruled out, but we don't know yet because we haven't processed it.
I was working on the subject. Actually, I started to work on a small just COVID. I have seen that there were different types of predictions, and where inflationary prediction is the only that survived were already in the 80s, and others that of course were wrong. To the observation of that's the ecological effects.
Even the first models of inflation were wrong. Right? They didn't work. They were a great idea, but they didn't work. When you calculate them, they fell apart, and people tuned them up. And so it's this funny thing where the theorists keep looking at the data and fixing it up, and then eventually they get the right idea, and then you can say, okay, right. But it's not like someone just sat down and wrote inflation theory down and said this is the right answer and I predict it. It's been this back and forth.
Of course, particularly the scale of inflation is something one gets from the observed value. The energy scale of inflation fixed with the observed value.
Right. In certain models of inflation, it's fixed by that. Some others you can flatten the potential and lower the, it's the combination of the derivative of the potential and the potential, so that depends on which model of inflection you use, you can keep adjusting, right? So some of them will predict a lot of gravity waves along with the density fluctuations, and some predict very little for the same level of fluctuations. And so that's what the experiment will do is to say which one of those models is more nearly correct.
Gabriele?
Yeah. Can you give us an idea of how sensitive Planck will be to tensor perturbations, or what kind of ratio of tensor to scalar it can measure? Do you have any guess about that?
Well, Jean Lamar, who's sitting next to you, could guess for you.
Or anybody.
The issue is whether you reach your raw sensitivity, which tells you the best you could possibly do, or whether there are either problems with the equipment or backgrounds that you didn't understand.
Yeah.
But, in principle, we should do about an order of magnitude better than exists now. But there could be 2 or 3 more orders of magnitude below that. It's plausible. Do you want to say more directly?
I would say that if the tensor part is at the higher limit of what we can expect physically now, Planck should be able to detect it.
I see.
Now we have to demonstrate that in flight, because that's the sensitivity of the instrument, but many systematics can happen in this type of measurements. And George has shown that, how important it was to remove all kind of parasitic measurements. And that's-
Foreground also.
Yes, foregrounds, and
Yeah, that would be very interesting.
I hope we can do something as beautiful and well reduced as you did.
Will you also measure Gaussianity,
Yes.
skewness?
Yes,
all
at a
of
high
these
level.
things, yeah.
We'll do everything we can. And then
Yes,
some
I
stuff
know.
we can't, right?
Yes, yes. Roger, Querem.
Yeah, many years ago I worked with Professor Chalonge on absolute photometry, and we used a homemade black body, I remember, for calibrating, of course, this intervention. I remember how hard it was possible to reach an accuracy of 2 or 3%. So I was absolutely amazed when I saw your error bars on the Kobe black body, which were, I understood properly, 400 sigma.
Yes.
And initially you said that you had to extract a signal from, I know it was 1 million times larger than the signal. So I think that is such an extraordinary achievement. Maybe it deserves some comment.
Yeah, I believe that it's technically just an incredible effort to do that. And to get that calibration was extremely difficult. So you can think of it this way, that if you hold your hand out, or you hold a square meter out, the cosmic background radiation gives you about a microwatt of power, whereas the sun gives you 1,000 watts. So it's like roughly 10 to the 9th in terms of raw power. So you're now trying to take that microwatt per square meter, and you're trying to decompose it over frequency. The nice thing about Michelson interferometer, it gives you the Fourier transform, so it gives you the frequency dependence immediately. And you cannot do it with an absolute measurement. You must do differential measurements. And so the issue was to measure the temperature of the internal reference extremely precisely, and that required using bridges, having comparison, basically they're platinum resistant, osmium resistant thermometers that were calibrated the National Bureau of Standards against other things, and putting them in bridges in controlled environments where you know that the boiling point of superfluid helium, you know the temperature fairly precisely, but that's still insufficient. And bootstrapping yourself up through absolute temperature calibration. And that's one way you get it. The other way you get it is the fact that you actually have a physical scale that relates your frequencies to wavelengths extremely precisely. That is, by having physically measured what the scan was and having a precise thing, you actually had an absolute calibration to know where the wavelength peaked in absolute value, so that if it were a black body curve, you know the temperature automatically from measuring where the peak is. And so it's a combined fitting to the fact that you have multiple, traceable to the National Bureau of Standards, now NIST, thermometers, and an absolute scale measured on distance that turns into a black body scale, that you cross-fit all those in order to make the measurement. But you're right, you could not measure it directly and see the answer. You had to have tuned your internal black body very precisely and have made that black body good to 4 nines, right, which is not good enough. And the external black body was designed so that it takes 7 bounces for light to go in and come back out, and the emissivity is much greater than 99% at each one reflecting. So 7 bounces gives you 6 nines or something like that, so that you're comparing something you think should be a black body against the sky, and you're comparing them against something that's the same temperature as the sky, so that every time you're doing just null differences. And yes, it is very hard, and yes, you have to be very careful and account for it. But if you want to actually be convinced, you have to go and read the papers and see how we try to account for all the various effects. And you have to worry about first and second and third order effects to be sure that you've got to that level. But the claim is we know the temperature at 1,000th of a degree out of 2.92 degrees, 2.72 degrees, sorry, 2.725 or something, 2.7. I've forgotten the last digits. It's only important if you're calculating how many photons there are per cubic centimeter.
Sergio con la francese.
Synergy Deutsche effect is going to become an extremely important role of the universe and cosmic structure. Not only in that it is able to probe the overall cosmological ground, but also to answer some fundamental questions like the nature of the particles or magnetic fields in the universe. But to do this from the theoretical point of view, you need microkelvin or maybe sub-microkelvin levels, an arcsecond to arc-minute resolution. Do you think that this will be achievable technologically in the next future? And which is the best strategy, ground-based observers or spaceport?
Right. Well, the South Pole or the Dome C are really good sites for trying to make these kind of observations because you're looking on a very small scale, and you can basically raster scan, right, and compare through almost the same amount of atmosphere, a very stable atmosphere. So it is possible to do that from the ground. To do it from space, you require a very large telescope, like something like James Webb, and as we all know, James Webb is extremely expensive. So you're not going to get a dedicated mission for that until we get much richer, right? We can afford it, So the ground-based is the way to go. And then the question is, how big a telescope can you build, and what is the science you can do, and how much is it considered worth doing it? But you certainly are down in sub-arc minute resolution with the South Pole telescope, and with that at the and with the apex at the highest frequencies. And then the question is, how many frequencies do you need in order to do the separations, if you can believe it well enough? And how many clusters must you see? Because a lot of the early calculations are doing assuming this clusters are spherical. We know clusters merge, there might be elliptical in shape. You have to you either got to study some clusters very carefully and understand them in detail, or you have to have a very large number of clusters, tens of thousands of clusters, so you can average out the aspect angles and so forth. And the second approach, I think, is actually going to be more productive in terms of getting scientific results out. But I think at the beginning, the SZ effect is going to be more about understanding clusters and about understanding the universe, but people will still try and understand the universe, but you'll have to prove that you understand clusters sufficiently well that you can use it for cosmology. I think it's all a question, it's technically feasible to do quite well. You just have to have funding and a dedicated team working on it, right? And that's the hard part. People get tired of being the South Pole.
I understand what you said about Sorbonne, but you don't say anything about the size of the telescope. Which size?
Well, the telescope you're looking at there are going from 10 meters to 30 meters.
10 to 30.
Yeah, they're quite large telescopes. And so it depends on what you mean. The working, you always under illuminate them, so the working part may be 10 meters, but the guard part may be out to 20 or 30 meters in terms of size. And so you're using that a little bit, but you're tapering the illumination so that you don't get full utilization of the edges. It's mostly to guard you against being fooled by spillover, right? I mean, this diffraction is an issue, right? And there are various ways you can approach that problem, right?
Please, Perrin.
I'm not a specialist of cosmology at all. I'm going to ask a very stupid question. Can you connect this 2D map with the 3D maps of the universe we have now? And is there any prospect to get a 3D map of the early universe beyond this?
Right. Okay, if you volunteer to be a grad student for millions of years, you can eventually, the light that's coming to us came from 13.7 million. It actually came from 370,000 years. You wait 1 year, it still comes from 370,000 years, it just comes from a light year further away. So if you're willing to observe the universe for millions or billions of years, you'll get a three-dimensional spherical surface around us where you have this information. Now, most people don't care to wait around millions of years, and millions of years is very tiny spot size, right? The million years this way is a tiny angle, right, on the sky, right? So you can do it. It's just a question of how long is your civilization going to last and so forth. But if you ask, what are we getting now? The difference between the Kobe map and the W map, which was several years apart, right, 10 years apart, that is 10 light years. 10 light years is just it's less than a spot, the resolution element in the picture that we showed you. So the human scale is such that the universe scale does not match very well. But if it was absolutely important, for the survival of the human race to map this over a billion years, right, then you would get a billion year thick, light year thick wedge around, the 15 billion years of the universe, you'd have a, instead of being the skin on the apple, it will be the skin on an orange, right? kind of matte. And you could say, well, what about present day? Remember, as you look out in space, you look back in time, right? So you're always looking back to the same time, and that sphere is just getting larger and larger. Every year it goes by, you get a light year further out. So the answer to your question is, yes, you can, but the other answer to your question is, you're not going to do it, and probably nobody else is, because they're going to move on to a different problem. Right?
It's just a continuation of other questions. Can you just briefly comment on the prospects for measuring primordial gravitational waves? Apart from transcan, specifically experiments that are designed.
Right. Well, there's lots of potential primordial waves, but there's one that a lot of us are really interested in because we want to know, was there inflation in the early universe? And one of the few theoretical papers that I've written was one that said if you measure carefully enough, you would see gravity waves from inflation, and that there would be a relationship between the tilt of the spectrum and the level of gravity waves relative to the density fluctuations. And that turned out to be true for a large class of inflation models, but not all of them. But there's a generic framework in which things set up. And the answer is, we don't know whether we'll see gravity waves or not. If the energy scale of inflation is high and the tilt of the spectrum is just a little bit, and WMAP is indicating there's some tilt, then there is a chance. And had there been early reionization, that also gives you a better window, because when you get to the larger angular scales, you get a confusion of the polarization from the polarization that's caused by the seeds being gravitationally lensed to look like the tensor modes. And so, the answer is, if we're lucky, if Planck does a good job and we're lucky, then we will see it, and if not, we will not. And there are a number of ground-based experiments like BICEP and polar bear and so forth that are coming along, also attempting to do it. It's something you may be able to do with a very good ground-based experiment. And if not, then you may have to go with an additional fourth space mission designed specifically to do that. And there's still no guarantee that you will see it, just because you have some fundamental limitations unless you figure out how to be more clever. So the question is, what we find along the way tells us how hard we're going to keep pushing. Right? But if I had to guess, I think the chances are sort of like 1 in 4 that we will detect the gravity waves in the next 10 years, right? And then maybe after that, they could either be missions that are a big version of LISA, big gravity wave event in space, or polarization missions that would be more sensitive and had a chance to see this. And so I think that it's such an incredible thing that people would really like to see this, because you would actually be seeing gravitons, not just gravity waves. I mean, it's kind of proof that you understand what's going on.
Are there any space missions that are proposed?
There is a NASA program called Beyond Einstein, and in it there were 2 big missions, Constellation X and LISA, and 3 small missions, the Joint Dark Energy Mission, the Black Hole Finder, and the Inflation Probe. And that was an extraordinarily good scientific package. I think all of those experiments are very good scientifically. Unfortunately, NASA has been given direction from our president to spend a lot of time and effort and funds on going to the Moon and Mars. That leaves much less money, that plus the fact that the shuttle has to keep running to get the space station finished, leaves much less money for science. And right now, NASA has had the National Academy of Sciences in the United States begin a study to decide which of the Beyond Einstein missions goes first. My belief is if it's one of the large missions, that basically stops anything from happening for 20 years besides that mission. And so I'm hoping it'll be one small mission and one large mission, and we can see, but I think in that situation it means that the inflation probe is put off fairly far into the future. Right? That's political realities as opposed to what would be the choice of science. Right?
One comment on this last question. I think that the problem of detection, the ultimate problem of detection of gravitational waves, I mean, or graviton, if possible. That is the one problem. I mean, it could be that technology, even, I mean, LIGO, LISA, I mean, this will take much more time than these cosmic microwave background experiments, which at least, even if they do not produce an effective detection, they will continue to place astringent upper limits on the ratio of gravitational waves to tensor, to scalar perturbations, or to density perturbations. And in this sense, in some sense, has the advantage of this cosmic microwave picture, together with the matching now of large scale structure observations, and so on, that the picture is going in progress in the sense that with COVID we had a first anisotropy detection. It was not clear at the time if it was inflation or other thing, as you told. But with MAP, already first year MAP, it appears a very clear indication, and your student, Alan Kogut, made in one...
He's more than my student now. He's much more advanced.
He
may be a kid to us, but he's a man now.
I mean, at the beginning, as you showed us, the data analysis of the younger one. Yeah. And then Alan Kogut, with the MAP team, first year, they detected TE correlation of temperature epolarization, which showed the right direction started to discriminate between inflation and alternatives because of the anti-correlation at L about 2000, which shows that all inflation, because topological effects goes in the antipodal direction of the data. It's not just adjusting parameter, but is inflation is the right direction, whatever the models will do. Now, with the next experiments, we could be able to, you could be able, experimentators would be able to detect or non-gravitational wave, but putting astringent limits already with the next map or on the tensor ratio, it will be possible to discriminate models in the right direction, inflation. So I think that, in this sense, the gravitational wave prospect, or the graviton prospect, presented by cosmic microwave background, is more for our generations. It's more reachable with the generations in that sense. The other, I finish and I leave because we have time. The other comment that I want to make is that I think at the time when you discovered the anisotropy, the large scale anisotropy, well, it was many explanations. It was the texture, the topological effect, and so on. But I think that you already keep in mind inflation. Even at that time, your prospect was, I remember, from your first talk, that you was pay attention to inflation, even if it was rough enough. But I think that, you was already in some, and then we got here, as you was in 2 years ago, in MAP first year, then we start to be in the direction of inflation. more clear picture from the experimental point of view. Morvan, Sanchez, and then
how many harmonics are predicted by models today, and how important would it be to be measured in future experiments? The highest harmonics.
How many? I'm sorry, I missed the first part.
I don't know how many harmonics are predicted by models.
Okay, well, what I forgot to say when I showed those harmonics, you actually multiply them by L+1 because there's the silk damping cutting off these harmonics. And so it comes down to sensitivity. There are many more harmonics that should exist, but because of the silk damping, the fuzzing out at the last scattering, their amplitude goes down quite substantially. So if you had a very precise measurement, you could measure them far out. But 7 is about all you can reasonably expect to get.
It's chocolate. It's not.
Show them the picture of Alfred Nobel. This one is lighter weight. It's not all gold. The center is chocolate. So thank you very much.
Thank you to you, George. As you demonstrate, I mean, we have not finished.
We're not finished, oh. I need to sit down. She's going to go on for a while.
Yes, you have water and chocolate to be, I mean, a little more patient here. I mean, you demonstrate with this, I am embarrassed because we need to celebrate you and to offer you, and you, as always, anticipate and make things before. So you make things before. But I would like to honor, I mean, your presence and the presence of so many. The kind presence of so many scientists here who came from different backgrounds, from different countries, from different institutions to be present in this celebration. We have some historic document from your first lecture in the course, made professionally by Monsieur Mouette, who did that for all the courses.
You have to connect the...
who made the registration of all lectures, and we would like to show you just some 3 minutes except
Oh God.
from 15 years ago. 15 years ago.
Was my beard white yet?
So you will see yourself 15 years ago, and then after we have also a historical, a very professional registration made by Arte Television, the European Arte Television, who was the filmmaker François for Arte Television, who did a film of the Chalonge School in which you participated, but I think you never saw the film.
No,
The film was transmitted in Europe, I mean, I can tell you, at a night called Thematics Night, devoted to Einstein, and we were supposed, I mean, presented by the journalists as the children of Einstein. I mean, those who are following, I mean, or using his theory to go in the understanding. So, please, if your passion is only just 3 minutes each, and then, so please. You will see.
This is Joe Silk.
Anisotropy
just accept your first lecture in Chalonge Medal, precisely. And the next excerpt is from 96, the art
En route pour les cours, à l'écoute des défricheurs de mystère, à la découverte des hypothèses de ses héritiers d'Einstein, le père de la cosmologie moderne. Fils spirituel de la relativité générale, les scientifiques utilisent toujours ces concepts. Mais ils entendent aller plus loin, en sortant la théorie de son aspect mathématique pour la confronter aux nouvelles données d'observation du cosmos. Si l'intitulé du cours est quelque peu obscur, rassurez-vous, les questions qu'il traite nous touchent. Qui nous s'est un jour demandé devant la beauté et l'ordonnance du monde, quelle est son origine et comment cette histoire a-t-elle commencé?
Well, we're here trying to learn about how the universe was formed, and we think we have a good idea, and we're trying to get more quantitative, and it's a very exciting time in cosmology, and particularly in the cosmic microwave background. That's the relic radiation left from the Big Bang. And we're studying it to make a picture of the early universe and to find out what happened at the very earliest times in order to understand how the universe came to be and how structures like galaxies, clusters of galaxies, and large-scale structures formed. And so it's a combination of a school and a workshop where we're trying to learn about all these things.
Moment essentiel dans la semaine de travail. De contact personnel entre chercheurs, postdoctorants ou étudiants, avides, curieux de rencontrer et de voir de près celui dont il a lu avec plaisir ou avec peine les articles, ou encore de pouvoir lui parler tout simplement. Aucune question, ici comme au cours, ne sera jugée saugrenue ou inopportune. Toutes ont leur valeur. C'est la règle du jeu.
I studied in Argentina. I did my undergraduate studies in Argentina. Now I'm doing a PhD in Leiden. And why I studied physics? I don't know. I think it's especially cosmology. I think it's something that it's deep inside you, and people, I think people who do cosmology have passion for it, and we cannot avoid it. I mean, it's what we like to do.
It's good. I'll trade.
So, because of that, we have also a surprise, something, to offer. We already got Nobel diploma, Nobel medal, Nobel award, but this course, as you perhaps remember, it was another Nobel Prize in astrophysics, Professor Chandrasekhar, who came with his wife, Letitia, from India, to celebrate and to inaugurate Daniel Chalonge, his friend, and he opening the course with the lecture Daniel Chalonge and the abundance of hydrogen. Today is a problem. The abundance of hydrogen is understood. It's established. At the time, it was not the case. It was very well explained by Chandrasekhar in the sense of encouraging pioneering work and being pioneering. And at the same course, many people, some of them are here. Mrs. Chalonge, now died, Chalonge, wife, offered me a medal called Daniel Chalonge Medal, which was coined in honor of Daniel Chalonge by the Hôtel de la Monnaie de Paris, which is a great honor for a scientist to have a medal coined by officially Hôtel de la Monnaie de Paris. And it was done after Chalonge died, because Daniel Chalonge was not, he didn't like too much honors, or have not searched, never searched honors. One side of the medal is Daniel Chalonge, and the other side depicts in two hemispheres the Orion constellation, studied at the time, among other things, by Daniel Chalonge, and in the southern hemisphere, the other part, is the so-called Chalonge peak, or Point Chalonge, because he liked very much I performed expedition and mountain, high altitude mountain, escalated mountain. And I wanted several times offer to you the Daniel Chalonge Medal. At the time I got from Mrs. Chalonge the Daniel Chalonge Medal, which one medal I left for the museum, in Erich, Museum Daniel Chalonge. The other I offered personally to Nobel Prize, and in recognition that he came in spite of his age, I offered to Nobel Prize Professor Chandrasekhar. Then after the medal Daniel Chalonge was exhausted, it was not possible to find other Daniel Chalonge medal at the Hotel de la Monnaie. Next year they will do a revision, so we will be able to have. But what is important that also your Nobel Prize inspired is that the artist, the sculptor, Mrs. Madeleine Pierre Querol, who is aged now 93. She knew that I was searching for a Daniel Chalonge medal to offer to the new Nobel Prize, and in a very generous action, she sent to me her Daniel Chalonge medal, her own medal. She's 93 in Paris. I wanted and said, I want to, then you will be able to offer to Professor Smoot the Daniel Chalonge medal. So, what I am offering you now, I mean, Daniel Chalonge medal from the, and which came directly from the person, the sculptor, the artist who did the medal. So with this value, I will. Other person who got at the time the Chalonge, but you have now the Chalonge.
It's hard to even say what this, I mean, this is very much a surprise. As much as a surprise as the Nobel medal, actually. I wasn't expecting it to be. This is a great honor. There's fewer of these than there are Nobel Prizes. And I've been attending Daniel Chalonge schools for many, many years. I felt really bad about missing this one, so I made the special trip for this one. I think it's a great honor both to attend the school, never mind getting the medal. So, thank you very much. She saved the bag too? Wow.
So,
Good,
Sevre, ça en a fini. On n'a jamais.
We start the guided visit of observatoire from here. I call Professor Suzanne de Barba, who will offer a quick comment of the room under the portraits of Laplace, Arago, Louis XIV. She will comment very quickly what we are in this historical room. Then we will take the photo of the group and go on for the guided visit. Journalists who will make interviews of Professor Smoot can then, during the visit, remain here or after we do the Grand Gallery, so of course we have time to see the little museum too, and then when we go to upstairs, we can stay if you like to make the interview. Okay. So, Suzanne, please.
I'm happy to see you again, most of you, I assume. Most of you have perhaps been in the last colloquium organized by Norma, last June and July, so the two will be the same. Nothing can be changed in the observatory from that time. In this room, which is nowadays the council room of the Paris Observatory, you have, as said by Norma, Louis XIV, who created it in 1667, and on his left you have Cassini. Cassini is the first, whose name has been given to the Cassini mission, who went to Saturn. We have not the three other Cassini, but after the last one, Cassini is the fourth, we have other successive people who have been at the head of the Paris Observatory. Lalande, Méchain, Delange, Bouvard, on the left in this door, Arago, Le Verrier, behind the screen, Delaunay, behind me, a new time Le Verrier, who came back, being 2 times director of the Paris Observatory. After Le Verrier, Tisserand in this window. No, excuse me. After Le Verrier, Amiral Boucher, who is there. And after the Amiral Boucher, Tisserand. After Tisserand, Louis. After Louis, Benjamin Bayot, who was the first president of the International Astronomical Union in 1990. After Bayou, we have had Esclangon, but we have no portrait in this room of Esclangon. No, after Bayou, excuse me, I forget Delange, who was the director of the Meudon Observatory at that time, and the two observatories, Meudon and Paris, have been mixed at that, under his direction, as being the Paris Observatory with two sections. After Delange, I forget Esclangon, and after Esclangon, from 1945, Danjon, who is in this window. After Danjon, we have had another director, he is there, Jean-François Delis, who has been not the last director, the one before the last one being Jean Delay, who died a few years ago. And after Jean Delay, the 2 last directors of the Paris Observatory, we had president of the Paris Observatory. One was there at the moment, the last one. And the ceiling, you want something about the ceiling? On the ceiling you have a painting which has been made in 1884, recalling the 2 transits of Venus over the Sun. Those from 1874, the second one from 1882. And if you look at it carefully, you will see, of course, the Sun, Venus, and so on. And also in gold, suggested to use the transit of Venus around the Sun for the determination of the parallax of the Sun. If you look at the right of Salé, you will see in silver Delisle, who was a French astronomer who, because perhaps you remember that Halley died before the first transit in 1761, and Delisle replaced him to call all astronomers to do that. And in front of him, he was the face of Leverrier, who has used the many transit of Venus and Mercury for his works in celestial mechanics.
I want just to say that we have also the portrait of Laplace, yes, who was not a director because he worked in science, I mean, not time to do an illustration, but we have here all the complete, le Sevre complete de Laplace. We are going now to proceed with the visit to take the picture and then the gallery, and mentioning Monsieur Denis, one of the former president and director, Jean-François Denis, president and director of the observatory. I recall a point of information which I want to give to you and to George, connected with what was done just about the medal 1 minute before. Madeleine Pierre-Querol, the artist and the make generous donation of the medal, was the student, the pupil of her maître in sculpture and in painting was the painting Denis, the father of Jean-François Denis here, post-impressionist painting, and who worked also with Jean Renoir. So, Pierre Auguste, the impressionist painter Pierre Auguste Renoir. So she make this comment. I think it's very important because she is 93. So we go now. We proceed with the photo and then we go to the content.
Ouais, Jean-François. Tu n'es plus incognito, même.
Non.
Ici,